Here's a number, 10 to the power of 22. That's how many operations per second you'd need just to simulate 1 million people. Not a planet, not a civilization, 1 million people. Now ask yourself, who's running the tab? The simulation hypothesis sounds like philosophy. It's actually a computational nightmare dressed in elegant logic. So either the civilization running this thing is basically a god, or there's a crack in the argument. We're gonna find the crack. Let's start with the logic trap. The simulation hypothesis says we might live inside a computer simulation created by some advanced civilization. It's the Matrix, but without leather and probably worse lighting. The modern, rigorous version of this idea was framed as a trilemma. Either one, almost all civilizations die before they can build ancestor simulations, or two, advanced civilizations have no interest in simulating ancestors, or three, we are almost certainly living in a simulation. If you reject 1 and 2, you're pushed to accept 3. Elegant, unsettling, and deliciously simple. But does simplicity equal truth? Not always. Before we judge, let's ask the right questions. What assumptions does the hypothesis rely on, and can those assumptions be tested? There are 3 big assumptions hiding behind the idea that we are simulated: computational feasibility, philosophical substrate independence, and the statistical argument about observers. But let's ask, can a civilization actually simulate a universe, or even just a paste of life like Earth with people and weather and coffee stains, without inventing magic? A lot of the drama collapses once you do some back-of-the-envelope math. The human brain is often the benchmark. If you can simulate a brain, you can simulate minds. A conservative neuroscience estimate gives us roughly 10 to the 11th neurons and about 10 to the 14th synapses for a human brain. If we store 1 byte per synapse, tiny, tight, and optimistic, that's 100,000 gigabytes, about 91 terabytes. That's one person's memory map at a synapse resolution level. Multiply by millions or billions of simulated people, and you're well into exabytes and beyond. If each synapse needed more complex state, milliseconds of potentials, ion channel states, detailed biochemistry, the cost skyrockets. But raw storage isn't the whole story. To run a brain, you need operations per second, synaptic updates, spike propagation, short-term plasticity. If each synapse updates on average 100 times per second, reasonable for many networks, then a single brain needs about 10 to the 16th operations per second. That's 10 petaflops of sustained computation per person. A lot, but not unattainable in principle for an industrial civilization with huge computational infrastructure. The kicker is scale. Simulating billions of brains, plus entire planetary environments at fine detail, is an astronomical, pun intended, computing problem. Okay, fun so far, but let's ask, can we test the idea scientifically? At first glance, no. A perfect simulation would be made to be indistinguishable from base reality, but the clever people don't stop there. Scientists and philosophers have proposed possible empirical signatures, subtle cracks that a simulated universe might reveal. I'll run through 3 main testable predictions that have been discussed in the literature and what they mean. Test 1. Discretization of space-time. If a simulation runs on finite resolution hardware, the simulated space might have a smallest unit, a lattice spacing, analogous to pixels. That could show up as violations of Lorentz invariance or energy momentum conservation at extreme energies. In the real world, we look for these signs in ultra-high energy cosmic rays and in the behavior of gamma rays. If particle energies show unexpected cutoffs or preferred directions aligning with a lattice, that could hint at an underlying grid. In practice, tests are hard and signals ambiguous. Physics experiments thus far show extremely tight Lorentz invariance, so this test has not yet revealed smoking guns. Test 2. Computation-Limited Anomalies, rendering shortcuts. In complex graphics, video games don't render what you're not looking at. Could a simulator save resources by rendering detail only when observed? That idea predicts observer-dependent decoherence or improbable correlations at the edges of observability. In quantum mechanics, measurement already plays a weird role. Some have suggested that looking for observer-dependent collapse anomalies could offer clues. So far, quantum experiments remain well described by standard quantum theory, but quantum foundations are subtle and contested, not an obvious smoking gun, more like a philosophical eyebrow raise. Test 3. Statistical signatures in natural randomness. If the simulation uses pseudo-random number generators for large stochastic processes, certain statistical fingerprints might appear: non-ideal randomness, patterns, or repetitions. For instance, if very large-scale cosmological fluctuations or extreme events show unexpected regularity, that could be a hint. But natural processes and chaotic systems produce patterns too, and finding a pattern is not the same as finding a program. It's easy to mistake structure for intention.
Now here's where things get really strange. What if the Fermi Paradox isn't about aliens at all? What if it's about the nature of reality itself? In a previous video, we explored simulation theory, the mathematics suggesting our reality might be computational, the statistical arguments that make it more probable than not. If we're in a simulation, the Fermi Paradox has a simple answer. The simulation isn't rendering other civilizations because we haven't encountered them yet. Think about video games. The world only loads what's necessary for the player's experience. Walk into a new area, and it renders. Leave that area, and it might unload. If our reality works this way, alien civilizations might not be rendered yet because we haven't reached the point in the story where we meet them. Or maybe the simulation is focused on humanity specifically. We're the experiment, the point of interest. Other civilizations exist in the code, but they're not active, not simulated, not real in the way we're real. This would explain everything. Why the universe appears fine-tuned for life, but we're alone. Why the Drake equation fails. Why we find silence despite overwhelming probability. The simulation has limited computational resources. Rendering one intelligent civilization is expensive enough. Rendering thousands would be unnecessary if the simulation is studying us specifically. But here's the disturbing implication. If this is true, then first contact might be scripted, a programmed event, a narrative beat, and we wouldn't know until it happens. Or maybe it never happens because the simulation ends before that chapter. Maybe the great filter isn't extinction. Maybe it's the moment the simulation terminates, when the experiment concludes, when the observers are satisfied, and reality just stops.
So the empirical roots exist, but all are difficult and ambiguous. Now some math to show the sort of reasoning scientists actually use when testing these ideas. Remember our earlier synapse numbers, 10 to the 14th synapses, roughly 91 terabytes at 1 byte per synapse. If we require, say, 100 updates per second across those synapses, that's roughly 10 to the 16th updates per second, roughly 10 petaflops. Multiply that by 1 million simulated people, tiny compared to Earth's population, and you need 10 to the 22nd operations per second. Those are monstrous numbers. The upshot, if the future civilization is running such sims, either they have unfathomable compute or they limit the simulation in clever ways: coarse-grained physics, selective fidelity, or partial realism. That gives us a clue. If simulations are being run, they're probably not perfect atom-for-atom recreations of entire planets. They're optimized. Which brings us to a powerful critique: Occam's razor. The simulation hypothesis often flips Occam on its head. Instead of positing a simple, elegant underlying reality, it posits a more complex infrastructure behind everything. Why not accept the simpler explanation that reality is real, unless there's good reason to posit a simulator? Proponents counter that the simplest statistical expectation given multiple ancestor simulation instances leads to the simulation being more likely, but that argument depends on debated priors. Bayesian inference is great, but garbage in yields garbage out.
Another philosophical crack appears in the idea of ancestor simulations themselves. If the goal of these simulations is to study history, they must be sufficiently accurate to produce the phenomena of interest. But many scientific phenomena are emergent and sensitive to tiny differences. If you fuzz out the microphysics to save compute, you might miss the very effects you'd want to study. So it's plausible that advanced simulators either simulate only what's needed, or they simulate at high fidelity but only for a tiny sample. Both options undermine the "we are almost certainly simulated" probability boost. Let's talk about falsifiability, because that's the heart of scientific respectability. A hypothesis that cannot be disconfirmed is not science, it's metaphysics. The simulation hypothesis can be made unfalsifiable by building simulators who intentionally erase evidence of their own existence inside the simulation. That's cheating. But if we restrict ourselves to the weaker claim that a simulation might leak detectable signatures, then it becomes at least partly testable. Look for Lorentz violations, search for anomalous cosmic ray cutoffs, examine statistical randomness in the cosmic microwave background, and scrutinize the quantum measurement problem. So far, no convincing leaks. Now for a thought experiment to sharpen intuitions. Imagine a future civilization that wants to study your neighborhood in detail. Not you personally, but social dynamics at the block level. It wants to run 1,000,000 Monte Carlo histories to understand how neighborhoods evolve. It will likely simplify, approximate molecules, simulate weather with fluid approximations, and model people as agents with compressed internal states. The simulation will be optimized for the questions the civilization cares about. That implies many simulations would be low fidelity in everyday details. You being conscious matters only if the simulation architecture preserves whatever substrate independence is required. That reduces the probability that your precise reality is a perfect, high-res copy. I promised jokes sprinkled in. Here's one. If we are in a simulation, at least the lag is not our fault. And if you see a frame drop, don't blame your ISP, blame the simulator's GPU. Back on the serious channel, let's discuss the astronomical number objection. A common reaction is, there could be 1,000,000,000,000 simulated minds, so probability skyrockets. But quantifying that trillion requires assumptions about future demographics, values, and ethics. Will advanced civilizations simulate suffering? Will they have reasons to run ancestor simulations? They might consider it unethical. Or they might find simulations boring and prefer other research. These are empirical sociological questions about hypothetical civilizations, not physics. We can't reliably assign probabilities to them. What about consciousness as evidence? Some argue that subjective experience feels real, and that such realism indicates a base reality. But that's a philosophical move. Your experience doesn't give a meta-ontological certificate. If you're simulated, you'd still have vivid experiences. That's the creep. The simulation hypothesis is consistent with virtually any observation you make inside the simulation, which makes falsification tough. So what is the best scientific stance? Skeptical, curious, and cautious. Simulation theory is a serious philosophical and occasionally scientific conversation starter. It has motivated, clever empirical proposals, which is good. The correct scientific attitude is to test the testable and admit the limits of the rest. If future experiments found Lorentz violations implying a lattice scale, or if cosmic ray spectra showed telltale anisotropies tied to a grid, that would be revolutionary. Until then, the hypothesis sits in a gray zone, interesting enough to discuss, but not yet evidence-backed. Now, every claim I have made in this video is mathematically specific and, in principle, falsifiable.
If you can resolve the exponential scaling problem, I want to see your argument. I have opened the Community tab for exactly this purpose. Subscribe to the Cosmic Codex for more arguments built on evidence rather than assumption. And the next time someone tells you we are living in a simulation, ask them one question. How do you plan to classically simulate a Hilbert space of dimension 2 to the power of 10 to the power of 80? Then watch them change the subject. Until next time, demand the math.